In section 9.3, we're going to be covering double angle identities as well as several others. So first of all, let's start with the double angle identities. We're going to be using these identities when you can notice that maybe the angle is not on the unit circle, but 2 times that angle is on the unit circle, and that would be helpful. So you would be rewriting these identities to notice that this is 2x, but when you look at the identity, in each one you have x. Okay, so let's look at an example of that and how we would use it. This one we have the cosine of x is negative 24 over 25, and we know that x is between pi and 3 pi over 2. We're going to find the sine of 2x and the cosine of 2x. And then we're going to show that that's between 2 pi, that 2x is between 2 pi and 5 pi over 2. Okay, so we'll start out just by making a sketch here, and you notice that x is between pi and 3 pi over 2, so that means that it's going to fall in our third quadrant, and I have a right angle and you have theta here, and so what that means is that we have 7 here, and actually we don't know that yet. Let's leave this. Okay, because the cosine is negative 24 over 25, then we have that this would be 24, or negative 24, and this would be 25. You also know that this would be negative, and use the Pythagorean theorem to find the length, the vertical length here, and you would find 7. Okay, so from that information, what we have now is that we also know that the sine of x is equal to negative 7 over 25. So that's some extra information, which we will need. Okay, and so now let's go through and look at the sine of 2x. Using the previous identity, it says that we have sine, it's 2 sine x times the cosine of x. And so in this case, we would have the sine of x is equal to, we know, negative 24 over 25. Okay, and so then we can take this, let's go from here, this is just kind of separate, I probably should put this over here, 2 times the sine of x, which we know to be negative 7 over 25, times the cosine of x, which we know to be negative 24 over 25. And then we just simplify that, and you would get 336 over 625. Okay, and so there we have the sine of x, or the sine of 2x. And now let's find the cosine of 2x. So the cosine of 2x we know can be rewritten using that identity as cosine squared x minus sine squared x. And so if we plug in those values for cosine squared x, we negative 24 over 25 again, squared minus, and negative 7 over 25. And simplify that to 527 over 625. Okay, and so now we have both of those. Alright, moving on, let's look at another example, a different way to use this. Actually, we're going to use, let's go forward one slide, we're going to use some other forms of cosine 2x. There's a couple other forms. So in addition to the previous example, or to the first slide that I gave you here, you've got cosine of 2x here, and that's the one we just used. But you also have 2 other options, and that's cosine of 2x is equal to 1 minus 2 sine squared x, and cosine of 2x is 2 times the cosine squared minus 1. And so this time we're going to work through an example, and we want to express the rule of the function f of x is equal to cosine 4x in terms of powers of cosine x and constants. So we only want to use the cosine x. And it can be power, so it doesn't have to be to the first power. It can be cosine squared, cosine to the fourth, and so on. And constants are okay to use. So we start out with f of x is equal to cosine of 4x. And knowing that I have my double angle, I'm going to rewrite this as cosine of 2 times 2x. Right? And then using that, and again, the identity that I'm using would be, let's go back over here. This is the identity I will be using for it. Cosine of 2x is equal to 2 times cosine squared x minus 1. Okay? So using that, I'm going to rewrite this. Here's my 2. Here's my x. My x this time is 2x. So that will give me 2 times cosine squared 2x minus, and then the minus 1 is outside of the parentheses here. Okay, now we're going to repeat that process. So again, I have a 2 and x. I'm going to use the 2 as the 2 this time and the x as the x. But in order to do that, it might be a little bit easier if I rewrite this as 2 times cosine of 2x squared minus 1. And that's going to help me realize what I need to do once I simplify that. 2 cosine of 2x, I'm going to replace it with 2 cosine squared x minus 1, and then close that parenthesis, and then bring out my minus 1. So what's happened here is all of this has been replaced with this. Okay. Now at that point, I'm going to leave my 2, and I'm going to go ahead and square this, which means I need to FOIL. Once I simplify that, I realized I would get 4 cosine squared x minus 4 cosine squared x plus 1. And then minus 1. And I see I have one sign. This is actually to the 4th power. And the reason that's to the 4th is because I would get this cosine squared x times cosine squared x and get cosine to the 4th. All right, now I can distribute my 2, and I get 8 cosine 4th x minus 8 cosine squared x plus 2 minus 1. And I simplify that one more step to 8 cosine the 4th x minus 8 cosine squared x plus 1. Okay, and there I have it simplified. You notice we only have powers of cosine x, and then we have one constant, the plus 1. So it's worked out. And moving on, let's look at another example. This one we're going to do a proof. And again, we're going to use the identity for cosine of 2x. You notice that we want to get a sign here. So this looks like the right-hand side looks like the simplest side. So what I'm going to do is to take this piece right here out, and I'm going to replace that piece with 1 minus 2 sine squared x. Okay. So when I do that, 1 minus, I need parentheses there because I need to distribute that negative. Okay, so that's my left-hand side, and when I distribute the negative, I end up with 1 minus 1 plus 2 sine x, sine squared x, over sine x. And once again, I can simplify and just get 2 sine squared x over sine x, and that's because 1 minus 1 would just give me 0. And when I simplify this, I would just end up with 2 sine x, because the sine x would cancel out, and bring down the other side equal to 2 sine x. And so we have completed the proof. And then the next we have is the power reducing identities, and these are exactly what they say. They reduce a power. So here you have a sine squared x, and it takes it down to a cosine, but a cosine to the first power. Here cosine squared x, but again it takes it down a power to cosine to the first power, but it does become a 2x in that. Okay, and we're going to look at another example. And for this one, we're going to express the function tangent squared x in terms of constants and first powers of cosine functions. So the first thing I'll do is I will take the tangent squared x and I will rewrite it in terms of sine and cosine. Okay, and once I'm there, then I can use the power reducing. So I know that sine is going to be 1 minus cosine 2x over 2 divided by the cosine squared x, which would be, its power reducing would be 1 plus cosine 2x over 2. And then from here we are dividing fractions, so 1 minus cosine 2x over 2 times, through the reciprocal of the other, 1 plus cosine 2x. Okay, at this point the 2's cancel, and then I end up with 1 minus cosine 2x over 1 plus cosine 2x. Okay. And then we have our half angle identities. So as we worked with the sine of 2x and the cosine of 2x and so on, here are the half angle identities and how they are used. We have them for sine, cosine, and then you can see tangent here, and then you also have these options. Alright, and this time we are going to work with a tangent of x is equal to 5/8. This 3 pi should be over 2, so let's put that there. Actually, I'll put that in a different color so it looks like it's part of it. Okay. Okay, so just like the last one, when we're working with tangent of x over 2, if we go back to look at the identities and you're looking here, you notice that you use cosine and you use sine. And so when we're working on this problem, then we need to use this, but also find the, we're going to use that to find the sine and the cosine so that we can use the half angle identities. Okay, so we start out here. We are going to be, to meet this condition here, we know we're going to be in the fourth quadrant, and so my angle looks sort of like this. Here's theta. We've got our right angle. We know that the tangent is 5/8, and so we have 5 and 8, opposite over adjacent. And using that, we can use the Pythagorean theorem, 8 squared plus 5 squared would give you 89, so this would be the square root of 89. Okay, so what does that give us? Now we know that the cosine of theta is equal to 8 over the square root of 89, and we also know that the sine of theta is equal to negative 5 over the square root of 89. And we know it's negative because it's in the fourth quadrant, and there the y-coordinate is negative. Okay, so from here we can find the tangent of x over 2. And we know that is 1 minus cosine of x over sine of x. Okay, and so we say 1 minus 8 over the square root of 89, just plugging in values here, divided by negative 5 over the square root of 89. Okay, again we need to do operations with fractions, but also we probably need to take that 1 and replace it with root 89 over 89, root 89 first, another form of 1, so that we have a common denominator, which would give me root 89 minus 8 over the square root of 89 divided by negative 5 over the square root of 89. Okay? And so now let's go ahead and divide those fractions. Multiply by the reciprocal. Okay, and this is convenient because then the square root 89's cancel, and we are left with square root 89 minus 8 over negative 5. Okay, and that is our answer. We have two more identities to look at, or two more sets of identities to look at. First of all, you have the product to sum identities, and these are exactly what they say. You've got a product, and if you were looking to take that product to a sum or difference, then we have these. Same with sine and cosine. And then you have a cosine x and a sine y. And then the last set is the sum to product. So if you have a sum and you want to take it to a product, notice here's your sum and here is your product. Okay. And that's all I have for section 9.3.